Okay. Welcome everyone to the 2020 Aspen Center for Physics Heinz Pagel's Physics Talks. This is an online version of the series that usually happens at the center. My name is Brian Swingle, and I'm moderating this evening's presentation by Professor Aharon Kapitulnik of Stanford University. So first, a few organizational points. If you did not receive the email of the lecture schedule or description of the lecture tonight, you can be added to the mailing list by contacting the center. This series of talks will be live online every Thursday evening at 5:30 p.m. Aspen time through August, and then posted on YouTube the following day. We will not interrupt Aharon during his talk, so you'll be muted, but there will be a question and answer session after the talk where you'll have a chance to ask questions. We also like you to know that the video image may be included in YouTube posting, so if you don't want to be seen, just please turn off your video. That's the easiest solution. For those of you who are not familiar with the Aspen Center for Physics, I'll just say that, as one of my colleagues suggested, it feels a lot like a summer camp for physicists, where we get to get away from the duties of university life, gather with a diverse spectrum of people, and explore really new ideas in a beautiful environment. This summer would have been my 5th time in Aspen, so I can experimentally confirm that it's a very special place, like everyone says. I would have been in a workshop that I co-organized with our speaker tonight and others on the subject of hydrodynamics and quantum matter. So we're very happy to see you here for a glimpse of some of the exciting science that we had planned to talk about there. I also want to point out that the center is partially supported by the National Science Foundation as an investment in the nation's scientific base. Now, our speaker tonight is Aharon Kapitulnik, the Theodore and Sidney Rosenberg Professor of Applied Physics at the Departments of Applied Physics and Physics at Stanford University. His research focuses on experimental condensed matter physics, and he is also opportunistically applying his methods to tabletop experimental studies of fundamental phenomena in physics. He's received a long list of prizes and awards, including the very prestigious Oliver Buckley Condensed Matter Prize of the American Physical Society in 2015. He's a fellow of the American Physical Society and of the American Academy of Arts and Sciences, and a member of the National Academy of Science. Tonight, Aharon's going to tell you about superconductivity and time reversal symmetry. And you probably won't be surprised when I tell you that superconductors are very complicated. In fact, even figuring out what questions to ask is not easy. Fortunately, one of Aharon's specialties is using clever experiments to really tease out the subtle properties of these very complex natural systems. He also hinted to me that his talk may help you understand a certain upcoming Christopher Nolan movie. So I think you're in good hands. And without further ado, take it away.
Thank you. Wait, am I sharing?
There you go. Yeah.
Am I sharing?
You're sharing now.
Good. So thank you everybody for coming. It's a pleasure. I will talk today about something that seems very complex, lots of buzzwords, but hopefully with some explanations, we will get to the punch. In fact, I'm going to start with the punchline. It's all going to be about time, and time is very important. Time is very important in many aspects of life. In rock and roll in particular, you can see one of the greatest songs of rock and roll involve time. We will see more of these later. In any event, before we start, let me tell you the punchline of this talk, so at least you'll see where I'm heading, okay? And in fact, you'll see also what led to the topic of this lecture. So we discovered in my lab at Stanford that there are some materials that when they become superconductors, and we will talk about these, then they are able to rotate polarization of light. So if this is a beam of light and the polarization is this direction of the arrows moving forward, bouncing from this superconductor, the reflected light rotates the polarization, which is really something very, very peculiar done by a superconductor. These are two examples of two materials, compounds. One is called strontium ruthenate, the other one is called uranium platinum-3. Doesn't matter, there are several other materials that do that. This is unexpected, and I want to tell you now about this phenomenon. Now, obviously, I need to connect it to time, and you'll see that this type of phenomenon of this rotation of polarization is actually interpreted as the violation of the symmetry of time inversion. And yes, it is a big deal. It is a big deal in physics. It is a big deal in condensed matter physics. And in the last slide, I will even tell you that it is a big deal in the future of quantum information science. So let's start. I'm going to divide this talk into parts. The first part will talk about time, then about time and time symmetry. In solid state physics, we are talking about solids. Its violation, especially when we discuss magnetism. Then the relation to light and how light is related to the probing of the violation of the time symmetry. And then superconductivity, and finally showing you this result that I already showed you, and hopefully by then you will understand my point. Okay, time. Like everybody else, I go to Wikipedia, and Wikipedia tells me what is time. That's the definition. The important thing for us is that it's a quantity that is used in various measurements, either to sequence events or to compare duration of events or to quantify rates of change of events. I mean, in physics, we use it as a quantity that help us to derive other concepts such as motion, energy, kinetic energy, time dependent of fields, etc., etc. Okay, light, for example, is a time dependent field. It's the wave of the electromagnetic field. Okay, so that's time. Time reversal is a transformation, and I'm going to denote it like mathematicians do with this script T letter. But just consider it that whenever I show this, I mean that what I'm going to do now, I'm going to take time into minus time. I'm going to go from going forward in time to going backwards in time. Okay, so therefore it describes time inversion. There is a movie coming soon. In fact, it's going to come in Europe earlier because Europe is open. Is going to be open before the US due to COVID-19. It's called Tenet. It's by Christopher Nolan. The YouTube of the trailer is written here, and it's basically, as you can see from the poster of the movie, it talks about time inversion. Time inversion, not time travel. Time travel is you go from one point in time to another point in time, either in the future or in the past. Time inversion is you trace yourself back in time. And I think the poster tells everything. Okay, so to make things a little bit more clear, I hope, there are other symmetries and other inversions that we understand maybe better. What about spatial symmetries and spatial inversion? So suppose I start at some point in space. I will denote it by x. That's the position in space. Then a spatial translation is taking x by translating it by some amount. I'll call it delta x, and I'm ending up at x prime. Okay. Now it is easy now to subtract this delta x from x prime, and I go back to x as I started, okay? So this is reversing the translation. And obviously I can do it back and forth and nothing changes, okay? So it's invariant under this process, okay? Now imagine now that we consider the translation in the time axis rather than space axis, okay? So I start with some time t, I add some time interval delta t, I end up at time t prime. And the reversal of the time will be taking now the same amount from t prime to get back at t. This is what I will call time reversal, okay? So, for example, you can watch a movie forward and backwards. The backwards is the time reversal of the forward. And here you see an example. I took a movie of Usain Bolt winning one of his races, and then frame by frame, I reversed that movie. And I'm showing you on the right that movie now going backwards. And you see that I'm tracing back all the frames one by one to go back in time. So this is going forward in time, and this is going backwards in time. Okay, so I talked about time reversal. What about time symmetry or time reversal symmetry? Okay, so this is the theoretical concept, which is the symmetry under this operation of t goes to minus t, of time goes to its time reversal. Okay. Sometimes it's called symmetry under the inversion of time. That is, forward and backwards look the same. This is going to be, for me, time reversal symmetry. Something is symmetric under time reversal if forward and backward look the same. Here is an example. I take billiard balls, okay, and I bounce them from each other, as you can see here. Now, I reversed that movie, which I created by myself, on the right. So on the left, you see the forward. On the right, you see the backwards. And the question is, of course, can you tell the difference? No, you cannot. In fact, here are the frames that I used. As I said, I created them myself. I reversed them myself. And I'm showing you now forward and backwards. I show you the point at which collision occurs between the two billiard balls. And you see that basically each frame has the mirror frame on the other side, which means that they are exactly the same. The reason is, of course, because there is no loss of energy in this collision, and time reversal symmetry is preserved in this process. Okay, take another example. Now I'm using squishy balls. Squishy balls are those balls that you know, they don't bounce very hard as the billiard balls. And what you see is that indeed they go, when they meet, there is a loss of energy, of usable energy, and they go back much slower. And the reason that they go back slower is they lost kinetic energy. They lost it to heat due to the collision, okay? Now, time inversion obviously cannot work. In fact, I'm showing you, these are the two frames before the collision. The collision occurs over several frames as the collision lost some usable energy. And then after the collision, this is the same time, but now it takes more time to go back to where they started, simply because they move slower, okay? Now, here I'm showing you both before and after, and obviously time reversal symmetry is not preserved. I lost energy. I cannot really imagine that the slow balls, squishy balls, as they collide afterwards, they will move faster, as I show on the right, okay? So here, this is impossible. That's before, that's the impossible. That's because time reversal symmetry is not preserved in this process, okay? Now, the billiard balls experiment is therefore symmetric under the reversal of time. The squishy ball experiment is not symmetric under the reversal of time. Therefore, I will say it breaks time reversal symmetry, okay? Now, our everyday life is more like the second experiment than the first experiment. In fact, time has an arrow. We notice all the time as we lose, a consequence of a loss of disposable energy. I mean, we get older. Even I get older. And this is just a consequence of the second law of thermodynamics, okay? However, the microscopic world is mostly time reversal invariant. For example, take Newton's law of motion. Force equal mass times acceleration, okay? F equal ma, as we all learned it in high school or even elementary school, okay? It remains the same if time direction is reversed. Why? Because the mass of an object stays the same, obviously, so it is time. Acceleration, well, acceleration, I remember now that there is a laser pointer. Okay, acceleration is the change of velocity with time. But velocity itself does not preserve time. It changes sign with time, right? If I apply this time reversal operator on somebody who is moving at some velocity forward, now he is moving with the same velocity backwards, that is the minus sign, okay? So since the velocity changes sign, now another change in sign because of this delta t in the acceleration leaves the acceleration time invariant, which leaves Newton's law F equal to ma invariant under the time reversal, okay? Now, there are quantities in physics that do change sign under the reversal of time, and there's those that don't. I mean, position does not change its sign under the reversal of time. It's just there. The force, we already gave this example, does not change the sign. Energy does not change the sign, or density of charge. We will talk about charged particles, so does not. An electric field does not change the sign. On the other hand, the velocity of a particle will change sign under the reversal of time. We saw that. Momentum, which is the mass times the velocity, will change sign, and electric current will show it, as well as magnetic field do change sign. And this is going to be the important quantities that we will discuss today in this talk, okay? But before I go to my field, which is condensed matter or solid state physics, let me just say, I have to say something about the universe, about the world where we live, okay? So there is a notable exception. I mean, I said that the microscopic world is mostly time reversal invariant, but there is a notable exception to that, which is the standard model of particle physics, which is what governs all physics that we know. And if you start from that theory, the so-called standard model, it turned that time reversal symmetry is not preserved in this model. Why did I write it as point number 2 and not point number 1? The reason is that we don't know what is the original theory of the universe, of life, of everything. So we call it nowadays beyond the standard model. For that one, we don't know if time reversal is preserved or broken. It could be that it is preserved and the appearance of broken time reversal in the standard model of particle physics is just an emergent phenomenon. This is kind of the thing that will always happen in condensed matter physics. And that's where we are. My third point is solid state physics, which is what I'm going to talk about today. I'm going to talk about materials, okay? On the microscopic scale, the description of solids is just the sum of all the kinetic energies and the potential energies of the ions and the electrons that make the solid. And if you write the energy, or the Hamiltonian as we call it, that governs the behavior of the solid, then it is time reversal invariant. That is, you change the direction of time on any equation associated with the solid, then nothing changes, okay? So therefore, if there is any time violation of the time reversal operation, it has to be some kind of an emergent phenomenon, okay? Well, there is one phenomenon, emergent phenomenon in solid state physics, which I can show you breaks this time reversal invariance. It is magnetism. And I think that by now we have some of the tools to understand why it does, Okay, so let me say a few words about magnetism. Okay, here is a magnet. These are the lines of the magnetic field. Let's talk about it. Well, first of all, you probably all know magnetism has been known from ancient times. It was known from when men first discovered this mineral magnetite, iron 3, oxygen 4, naturally found in nature, and found its peculiar properties. Now, I will be interested in some aspect of magnetism, which is the relation between electrical current, you know, the current that flow in the wires that you have at home, and magnetism, okay? So it turns that while magnetism itself was known for a long time, it took time before people understood the relation between electricity and magnetism. Ørsted was the first to discover that there is a relation between electric current in a wire and the motion of the needle of a compass. Compass was known for a long time, much before that, was used for navigation. Ampere discovered that a circulating closed loop of current is related to the flux that is associated with the magnetic field associated with that loop. And Biot and Savart were two people who give a quantitative equation that related the magnetic field associated with a current loop, okay? Okay, so there is some history here. So let's try and understand this relation, okay? Recall that velocity is a quantity that under the reversal of the time is going to change sign, okay? So it goes from velocity, let's say, go in one direction to velocity goes in the opposite direction, okay? Now I'm going to apply it to electric current. Electric current in a wire, so the current is the product of the charge times the density of carriers that I have, say electrons in the wire, times the velocity, which means that if I apply now this time reversal operator, that is, I enforce time reversal to the current, I'm gonna get current going in the opposite direction. So time reversal on current gives me current in the opposite direction because it's basically giving this property from the, getting this property from the velocity that changes sign upon applying this time reversal, okay? Okay, in that respect, let's look at a loop of current. So here is a loop of current. You can see on the left. It gives me now a magnetic moment, which is, as I said, was first discovered by Ampere and then equation by Biot-Savart. If there is a current I going in a loop, there is going to be a magnetic moment associated with it. And this magnetic moment is simply the current, which you can see here, moving electrons around, times the area enclosed by the current loop. Because current under time reversal is going to change the direction, because the velocity changed the direction, you can see here on the right, I changed the direction of the velocity. So here, instead of going counterclockwise, I'm going clockwise. Then the direction of the moment, because the moment, the magnetic moment is the current times the area does not change. The current will change its sign to become minus current, and therefore I get minus, or the opposite of that magnetic moment. On the atomic scale, I can look at a unit cell of the solid and assign a magnetic moment associated with these little currents moving there, okay? So on the atomic scale, I'm gonna have tiny magnetic moments, and these magnetic moments can be either one direction or another. And if I put them together for creating a solid, I have a magnet, okay? Here I put many, many such moments together to create a solid that has this macroscopic large number of magnetic moments that together create a magnet, and this magnet gives me a magnetic field. So 2 lessons. One is the magnetic field is associated with circulating currents, or with currents, in fact, in general, and that a magnet is just a collection of such microscopic circulating currents, creating moments, and these moments all add up to give me the magnet, okay? Obviously, if one loop is one moment breaks the time reversal symmetry, that is, violates the time reversal, because if I apply the time reversal operator to it, it's going to change direction, then the whole solid that has the moments pointing in the same direction is going to violate the time reversal symmetry, okay? So a magnet actually violates the time reversal symmetry if I change the direction of its magnetic moments. Okay, let's talk about light, because I'm going to use light, if you remember from the punchline with which I started this talk, okay? So here is light. The light now is propagating, as you can see, in the plus x direction. That's the direction of this arrow. That's the propagation direction. Let's just concentrate, say, on the electric field. That's the blue part, and you see it propagates forward, okay? Now, just like I did with the collision of the balls, I can take this movie and frame by frame go backwards, which I did. And this is it. It goes backwards, you see? But backwards means that now it goes into the minus x direction, where the polarization, that is the direction of the electric field, this blue, thick blue arrow, did not change. Now, I am sure that just like to me, also to you, it reminds very much like using a mirror and reflecting this beam of light from a mirror. So here I have going, let's call it forward in time. Then I'm going backwards in time. I did it frame by frame, just like we discussed at the beginning. But it looks like I used a mirror, okay? It looks like that. It looks that if I take a beam of light, this is now stationary, and I reflect it from a mirror, I get the same beam with the same polarization of the light, now going backwards. So I can use the mirror to go back in time for light, okay? And this is going to be at the heart of the experiments that we are going to do, okay? Okay, so if this is what a mirror does, this is what a magnet does. It does something very peculiar. Remember, a magnet breaks the reversal, this symmetry of time reversal, this time invariance, okay? And how do I see it? Well, it was discovered by John Kerr in 1877 that if he bounces light from a magnet, then the light that is reflected is not coming back like from a mirror, the same beam just going backwards. It is actually rotated. The polarization of the beam is rotated, okay? So this property is a manifestation using the light of the time reversal violation of magnets, okay? I can use now the light polarization to test whether a material violates the time reversal property or not. And indeed, it was done by John Kerr in 1877 to show that magnets violate the time reversal property of other materials, okay? Okay, superconductivity, I need it in order to come to the punchline. Okay, superconductivity, before that, let me just give one slide and you know, just take it at face value about electrons in metals. Electrons in metals obey the so-called Fermi-Dirac statistics. They are fermions. And in a solid, they occupy energy states in bands. These are, I mean, the different materials will have different band structure, and the electrons will fill the bands, and they will fill it such that no more than one electron in any state, and therefore they will get to some state, to some energy that is the highest energy after you filled with all the electrons that were at your disposal. And this highest energy is called the Fermi energy, okay? Now, for the purpose of discussion here, let's assume that this highest energy is a sphere, and I can now draw it in some space. I'm going to call it the momentum space. So think about this sphere as full with with electrons, okay? States of electrons. They are all filled until I got to this last surface, which is called the Fermi surface. Okay, that's one slide on electrons in metals. Now, in 1911, Camerly-Onnes took metals and tried to measure their resistance to flow in wires, that is the resistance of the wire of different materials. And he discovered that mercury below a certain temperature loses its resistance, okay? The resistance plunges to zero. As you can see here, this is from Camerly-Onnes' notebook, lab notebook. He received the Nobel Prize a couple of years later for this discovery. And basically, we are talking about the fact that the resistance below a certain temperature, we will call it Tc, that is the critical temperature for becoming superconductor, then the resistance vanishes. No resistance to flow of electricity in the wire, which is very peculiar. You know, if you take any electrical wire at home and you just hold it for a while, you'll feel that it gets warmer. That's because there is dissipation. But no, he discovered that mercury below that temperature is flowing electricity without dissipation. There is another important phenomenon that was discovered in 1933 by two guys, Meissner and Oschenfeld, that in fact, in that state, below that temperature, also a superconductor will expel the magnetic field from its interior. So if you apply magnetic field to any material, then there is going to be magnetic field everywhere, including in the material. On the other hand, in a superconductor, it does not allow the magnetic field to enter the superconductor. And if the superconductor is also a magnet, very peculiar things happen. I'm not going to talk about these today. Now, in 1956, in trying to explain superconductivity, Leon Cooper came with the notion of Cooper pairs. That is, despite that the very large Coulomb energy, that's the repulsive interaction among electrons, then on that Fermi surface, that highest surface of highest energy of electrons that electrons occupy, then on that surface, there is some instability, and electrons interact and attract each other rather than repel each other. And the interaction, which is by now you can find it in many different movies that people produce, is basically you start with an electron that polarizes the crystal at some point, and then at some subsequent point in time, another electron comes because now this region is more positive, the electron is negative, and it attracts the second electron, okay? That movie on the right tells you about, how it looks. These two electrons, one comes, the other follows. These are called Cooper pairs. And from this movie that I show you here, you see that this is very simple. In fact, there is nothing happening in the center of mass of these two electrons. So these two electrons are just moving, okay, together nothing is happening in terms of motion between the two electrons, okay? We say that there is no motion in their center of mass. Now, I'll come to it in a minute. Now, this was not the theory of superconductivity. The full theory of superconductivity that was based on this Cooper pairing, pairing of two electrons into Cooper pair, was constructed by Bardeen, Cooper, and Schrieffer in '57. They received the Nobel Prize for that in '72. And it explained many properties of superconductors. In fact, many properties, not those that I'm going to come towards the end, because their theory will not apply. Why? Well, it turns that in 1979, a German physicist, Franz Steglich, discovered a new class of materials that seems to not obey all the properties that Bardeen, Cooper, and Schrieffer predicted and were established for normal superconductor. If you summarize, and I don't have time to discuss all these interesting materials, they are called heavy fermions for some variety of reasons. The important thing for us is that there is magnetism lurking in the background, despite the fact that the material has no magnetism, okay? But there is some kind of magnetism which was not understood at the time, its relation, certainly not its relation to the superconducting state. Okay, so I told you about the fact that we are interested in these electrons at the highest energy, this so-called Fermi energy living on the so-called Fermi surface. Let me take a cut on this Fermi sphere that encloses all the states of the electrons. Here is a cut. And then this is the shell that I'm talking about. And it turned that these electrons that are going to pair together within this BCS theory, BCS formulation, are all living here in this state, and any other point on this sphere looks the same, okay? It turns that also you take such a superconductor, you bounce light from it, nothing. It's like a mirror, nothing happens. But it turns that these materials that were discovered by Franz Steglich have different types of pairing. So if this is the shell of states on a normal material, normal metal, normal superconductor, then there are all kinds of new type of shells on these new superconductors, which are now called unconventional superconductors. They cannot be explained by the Bardeen, Cooper, and Schrieffer theory. And not only that they are different in shape, but they have different phase such that not one part will look like the other, okay? So this is interesting, and there are questions whether new phenomena can happen because of that. Well, it turns that yes. And here I'm taking, now we are very close to the end, a particular material, strontium-2 ruthenium-04. It's a strontium ruthenate, a material that it's actually quite common. You can, I'm looking now at a single Cooper pair that is going to reside in these lobes on that surface of the Fermi surface. And then to my surprise, well, not my only, but everybody's surprise, it seems like it behaves as if the Cooper pairs are now creating their own loop of current. So you remember that for BCS theory, that the Bardeen, Cooper, Schrieffer, the simple one, I showed you the two electrons are moving together. There is no structure in that center of mass of these two electrons. That is, these two electrons are moving, nothing is happening between them. But here, in this new type of superconductors, something is happening. Every Cooper pair is now having these two electrons circulating in a circle, just like a mini magnet. And in fact, you can have it in either direction. They can circulate in one direction, creating a mini magnet of Cooper pairs, of pair of electrons now in one direction, or creating a mini magnet. So this is something new. A Cooper pair, instead of being kind of a vegetable just moving there and nothing happens, is now creating some kind of magnetism. Well, here's the punchline. Indeed, if you take light, and I already showed you that light can probe whether there is magnetism there, and you bounce it from such a material, and here I'm showing you results on the strontium ruthenate and another one on the uranium platinum-3. I bounce the light with one polarization, it rotates just like a magnet, but it's not a magnet. It has Cooper pairs that are creating small moments, and therefore it appears only in the superconducting state, not like iron that it's just there. So here it is, this is data. This is this angle of rotation of polarization as a function of temperature. This is real data, and it happens only below here 1.5 Kelvin when this material becomes a superconductor. For this other material, uranium platinum-3, it happens only below 0.48 when it is become a certain type of a superconductor. Now, if I find or prepare, and I know how to, this material with the opposite direction of the Cooper pairing, Cooper pairing circulation, like that, then the direction of the data reverses. So really, this shows that it behaves very much like a magnet. And by now we know what it means when light hits a magnet and bounces back with rotation of polarization. That material, the state of that material breaks time reversal symmetry. And this is unusual. Okay, so what did we cover today? First, the concept of time and time reversal symmetry, time reversal symmetry in solids, and occurrence of magnetism. Then some basics of superconductivity, a little bit on unconventional superconductors, and then this not expected property that some of these unconventional superconductors show effects like magnetism. Despite the fact that they are not magnetic, they show effects very similar to magnets, and these are interpreted as their state breaks time reversal symmetry or violates the time reversal symmetry in that superconducting state. And I promised that there will be one line on why do we care? Well, we care a lot. It turned that there are a lot of future applications in quantum computing and quantum information systems that rely on this property of superconductors, not of magnets, of superconductors that breaks this time reversal symmetry. But this is a subject of another talk. So thank you. And in the words of my favorite band, Pink Floyd, the time is gone, the song is over. Thought I had something more to say, but I'll stop here. Thank you.
All right. Thanks very much for that very nice talk. And now we have time for questions. So the way this works, if you have a question, please click the raise your hand button at the bottom of the screen and I will call on you. If you can't find the button, just send me a message in chat and I will just try to call people in order so that everyone gets a chance. So we give people a chance now to raise their hands. As people are raising their hands, we have a question from Robert Cooper. Do you want to unmute yourself and ask your question, or do you want me to? You're welcome to ask it if you like, or I can do it for you. Okay, well, Robert Cooper wants to know, is energy conserved in your experiments with time reversal?
Okay, so the experiment, the experiment itself of bouncing light and coming back, then there is always the light as it interacts with the matter, there is always absorption, and therefore no, energy is not conserved. But this is not part of that phenomenon. I mean, anytime light bounces from matter, there is absorption in the matter, and therefore energy is lost. But we are not. I mean, the phenomenon I was talking about has nothing to do with that. So from that point of view, the Hamiltonian of before and after or the state of before and after is the same, except for the polarization got rotated.
All right, great. Thanks for the question. Next, we have Wolfgang Ketterle.
Uh-oh.
Yeah, hi, Aaron. My question is, if you have a ferromagnet and you would cool the ferromagnet below the Weiss temperature, and it would suddenly have a magnetization.
Yes.
The fact that the magnetization points in one direction is also a reversal, is also a violation of time, is a time.
Yes.
Is a time in time reversal symmetry broken state. Right. So my question is, the fact that the Cooper pairs are in, have sort of right-handed L+1 or L-1,
yes,
or px plus IPY or px minus IPY, is it exactly the same kind of time reversal violation, or a spontaneous breaking in a certain state which assumes
unlike
direction, or what is the difference and what are the common denominator?
So the superconducting state is a coherent state of a condensate, where the magnet is I mean it's a macroscopic state, but it's not. I mean, I didn't explain all the stuff about superconductivity. Of course, the Cooper pairs, they are not pairs that are now moving around. I mean, in fact, they are changing all the time. It's a macroscopic state of all the electrons that at any given time you'll see them as pairs, and at any given time you'll see them as pairs that are paired in this particular state. But except for that, there are people that call such time reversal symmetry breaking superconductors. They call them superconducting magnets. Yeah.
All right, thanks for the question. We have another question now from Noah Breali. Noah.
Hey, Brian.
Hey.
Yeah, Aaron. Aaron, you know how fads are and how our communities follow not just condensed matter. There's other fads. Even in cold atoms, they've been following this condensate fad for some time now. So recently, there was a March meeting in 1987, and there were these new transition metal superconductors discovered, a little bit higher temperature than the heavy fermions, these cuprates.
Yep.
And I'm telling you what you already know, these cuprates, they're just no good. They're just hard to work with. But I wonder if we chose to be so brave and to look at the parent compound, say lanthanum cuprate, the original thinner, or I guess it was lanthanum baryon cuprate. They have around room temperature, 300 Kelvin, let's use some scale, around room temperature. They have a funny phase that, I want to use the word that it breaks time reversal symmetry, but the picture somehow looks very different. When I try and draw a picture in my mind, it seems it's an anti-ferromagnet, like many transition metal oxides.
Right.
There's no net ferromagnetic moment. And in fact, if we take like a model like something simple like Heisenberg wrote down in the 1930s, thinking about some trivial thing like nuclear physics, what we find is, say on a square lattice, some trivial lattice, simple lattice, that the ground state, quantum mechanical ground state, has rotational.
By the way, an anti-ferromagnet breaks time reversal symmetry as much as a ferromagnet.
That's what I'm asking. So what my concern is this: if I you know I'm a theorist, say, you know, like Brian, you know, and I go on my computer, because that's how we do all day, is stare at computers, and I write the Hamiltonian, say Heisenberg's boring Hamiltonian on a square lattice.
Yes.
With some boundary conditions I won't tell you because that's the secret of sauce, the secret sauce.
Okay.
And I find the quantum mechanical ground state. I assure you from experience, Brian can tell you in more detail, I'm sure, you can follow with him, not me, that the quantum mechanical ground state is rotationally invariant. It's what we call a singlet, like in a covalent bond.
Yeah.
You know? So my concern is, when does the cat choose to point in one direction or another? If I have my cluster on my computer, it tells me the cat is both alive and dead. It doesn't choose one direction or another. Talking about an antiferromagnet now, where the order parameter doesn't commute with the dynamics, you know. Ferromagnet, of course, is different. Your experiments are obviously very nice and correct. But suppose I shine light on lanthanum cuprate, and I make it smaller and smaller, the piece. It's an insulator, you know. Superconductivity is too fancy. At what point does the signal go away because the system is both up and down and alive and dead and all that silly quantum mechanics business that Nail said?
I mean, if
this just proves quantum mechanics is wrong because it doesn't describe my Nail state.
But even without quantum mechanics, you take an antiferromagnet, and you shine it with a beam of normal size, I don't know, a few microns. Then the experiment that I described will show zero. And the reason is that within this beam, there is going to be a macroscopic number of moments pointing up and moments pointing down, and they average to zero. But
okay, but you know, I mean, I'm beginning confused. I'm talking to someone who really does experiment. I mean, like I can do a neutron scattering experiment, right?
Yes.
And for example, your colleague.
So in Newton's, then
your colleague did one that I did my thesis on.
With Newton scattering, you can find antiferromagnetism. And so your question is, why does it choose one and not the other?
Yeah, so I thought I was asking about optics, but now I guess I'm asking about neutron scattering.
Okay.
So why does it choose one or the other, given Brian's results, given that Brian says it shouldn't?
It shouldn't what?
Brian, on his computer, he can tell you the details. He says that the ground state of, say, the Heisenberg model for an antiferromagnet is a singlet, like a covalent bond. It doesn't choose any direction. And no matter how big he makes his computer, and he has a big one, it always comes out singlet, assuming he has an even number of sites and some details and so on.
I mean, what do you mean by singlet versus? I mean,
well, take the language you use for the Cooper pair, right? So the Cooper pair with the S wave, we say it's boring.
You're talking about a superconductor on top of an antiferromagnet? I don't understand.
I'm a simple man, just an insulator. But I mean, singlet, they say it's talking about there's one state, it doesn't have any other directions it can point that it's symmetric with. It's just a boring, like a spin rotation invariant state, like the S wave state in atomic physics.
You get singlets instead of a macroscopic antiferromagnetic state?
That's what Brian tells me. I keep telling him to get a bigger computer, but every computer he gets, it's finite.
Okay, I'm not fighting with the greats Brian? Like Noel and others.
But I get it. If we do it with the spot size of a micron, there'll be some domain where it's up and some domain where it's down. The point, though, of course, is we can do what your colleague, he was a graduate student, Owen Vick, did under Grevin. Maybe this is why he didn't get tenure. I don't know. Anyway, with a neutron scattering, you can see a staggered moment. And so there's this problem that there's this conflict between people who
you see a staggered moment, and you see that there is an antiferromagnetic order. It's not just a collection of singlets.
Well, I mean, it's a collection of spin 1/2, let's say, electrons, you know? But then when he puts it in his computer and he uses the Heisenberg interaction that says form a singlet on each bond, then the collective state has zero, it's a unique state, it's non-degenerate, and it doesn't have any direction it prefers. And you can make it real, so it doesn't break time reversal symmetry.
A spin liquid. An RVB state is such.
Well, we're poor men.
We may be getting off track here.
We're poor men. Brian's going to try and correct you, but we're saying just a square lattice, just a boring old square lattice. No fancy frustration or anything fancy.
No, I think this goes really beyond the scope of this talk.
Yeah, I think thanks for the spirited exchange. Wolfgang wants to say something else. So.
Yeah, let me chip in, because when we did Bose-Einstein condensates, which were not prepared with a given phase, but then we interfered to Bose-Einstein condensates, we always found a phase. So what we learned, it's a little bit different from how people formulated it in condensed matter physics, but in quantum optics and atomic physics, we learned that the symmetry broken state can be regarded as a result of the measurement process. In other words, if you have a perfect ferromagnetic material and you cool it down and it becomes ferromagnetic, the magnetization can point in any direction. We have full symmetry, and this is what Noah mentioned, full symmetry on the computer. But the moment you make a measurement, you find symmetry.
Wolfgang, this is for a superconductor, that's normal. A superconductor breaks U1 symmetry, but you don't see the phase. If I just have a piece of superconductor, you don't see the phase. However, if I take these two superconductors and put them together very close to create a Josephson junction, then I will see the phase, because each one, I mean, there's going to be some phase difference between them, and that's what I'm going to see. So I think that what you describe is just that. So,
but similarly, you can probably say that your P-wave superconducting material, if everything is perfectly symmetric, the Cooper pairs are in a superposition state where they are all in, positive and negative chirality, and it's only when you shine light on it, when you do the measurement, you eventually force the system to decide and create spontaneous symmetry. So in that sense, one can actually say, one can treat materials completely symmetric, and what Noah says, everything is in a completely symmetric state, but it is then eventually the nature of the quantum measurement is projecting on one of the possibilities, and that's the symmetry broken state.
So it could be that if you take a gas and you impose this P plus IP on the gas, that's what you'll get. Except that now this gas of electrons that are now the superconductor are in a particular solid. There is some order parameter that complies with the solid in which these electrons live. And therefore, you cannot have such a situation. If there is a macroscopic order parameter, for example, for the P plus IP, it has a direction. For example, in strontium ruthenate. And this direction is a macroscopic direction associated with the whole phase. So you cannot actually have one or the other mixing on a microscopic scale. You can have breakdown into macroscopic domains, that's for sure.
Great, okay. We have time for like one more question if anyone out there has a burning question.
Maybe a question about the last slide.
Yeah, what is going on here? Noah has raised his hand again, so we'll give you another shot, Noah.
About the last slide, Brian. So
okay, all right.
Okay, so if we have a macroscopic ruthenate, real ruthenate, it has some spin orbit coupling. It points in a direction. Okay.
Yes.
What about a quantum computer? Like, say we make a quantum computer out of strontium ruthenate. How many qubits can we make before it just decides to stop being in a cat state and stops computing and just says, look, I'm going to point up, and stop computing?
I mean, honestly, I think that I cannot answer this question because I don't even know how to make a qubit out of strontium ruthenate. All I know is that in the field of protective quantum computing, people are talking about using materials with P plus IP that is the state of the superconducting state of strontium ruthenate, and there are schemes on how to do that. I cannot now repeat that scheme and or defend it.
All right, great. Thanks everyone for coming out. That's it for this evening. Thank you for the great talk, Professor Kapitulnik. Thank you for the Aspen Center to host.
Thank you, everybody.
And Next week's talk will be In Hot Water, Our Changing Polar Oceans by Andrew Thompson of Caltech. So see you then.
All right. Thanks. Bye.